All right, let me. So just timeline where we're at. We're almost to the end. So we just have half of this last chapter here to finish, or more than half, or whatever. So I don't think we'll finish today, but maybe. Then we just have the first and the third, and then the final, if I remember correctly, it's obviously the next week, but I think it's on the 10th. So I think it's Wednesday, a week after our last day. So the third we'll definitely review. There's a final study guide up on the Lima. And then there's always those worksheets. So maybe if we aren't done, we'll split the first next Monday between the lecture material and say the worksheets, and then we'll save the study guide for the third. Okay, hold on, I've got this error message. There, weird, it's gone. All right, full screen. Okay. So this whole part here is an expansion, right? It's chemical bonding, but it's the second half of it, and this is OChem, the beginning. A lot of this stuff, it'll be condensed, but you'll see the first week of OChem. They'll basically fly through these last two chapters and pulling out the stuff that they want to focus on, which is kind of what we've done, right? We didn't talk about the d orbitals or f orbitals, which they will never talk about because carbon doesn't ever use them. And then we're going on here to the next theory. So Lewis is the sort of the theory is the basic theory. So you can see that here, good first approximations. Resonance, but it fails in some of these electronic behaviors and a few other things that we'll see. And paramagnetic versus diamagnetic means, remember from last chapter, an unpaired electron. Right. And so this theory is called valence bond theory. For us, it's not a history exam, so don't worry about Linus Pauling here. And we skim the surface of the quantum mechanics and the numbers, and then we talked about the bonds in these atoms and the orbitals and the way they interact to make these bonds. But it depends on what's going on with those orbitals. The S and the P are the ones that are critical to us. So what we're going to get into now is, what we were doing before, those S and P, that was just the orbitals of that atom. But except for the noble gases, not everything else is a molecule. And we saw this previously, the last chapters, where the electrons come together and make the bonds. Now, if the electrons are moving in orbitals, then it's really the overlap of these orbitals. And electrons are moving throughout the whole molecule. We saw that in resonance. So it's really no longer an atomic orbital, it's a molecular orbital. We know that these molecular orbitals are more stable. Otherwise, you wouldn't make the bonds, right? So there isn't just a separate atom, like except for the noble gas. And they pair up. All right, so the interaction between atomic orbitals is negative, but when you interact atomic orbitals together containing two, then you get the molecular orbitals. All right, so let's say we had H2S, right? The S would look like this from our previous example. So the s, 2 electrons for the s orbital would be in here we see these two, right? Then a filled p, and that would imply this type of, p, x, y, and z. 1 electron from each p overlaps with the electron that the hydrogen brings. And so you see this, it would predict this type of thing, right? There's the s, you make a bond, the 1s from hydrogen, you make a bond. And this would predict roughly 90 degrees. And it turns out that it's around 92. So this sort of seems to work in this example. But this isn't what we see for carbon, which again, now you can see this is the basis for OChem. So what happened was that the number of partially filled or empty atomic orbitals did not predict the number of bonds or orientation of the bonds. So that worked for the H2S in that example. And so if we think about carbon, you should have something like this, 2s2, then the 3 different p's, doesn't matter, x, y, and z, which one, but 1 electron in each. And this would tell us only 2 or 3 bonds and roughly 90 degrees apart. And that's not what happens. We get that tetrahedral structure, 109.5, 4 bonds. So the model fails there. And the model that comes in place of it is this hybridized one. So, you've heard of a hybrid car, that's gasoline and electric. And that's the same thing that this new valence bond theory model that we're going to talk about and use, and for bio people that you will use for OChem all next year or whenever you take it. And what it does, right? Hybrid is a mix. We're going to now mix the 2s and the 2p, or you can just say the s and the p, right? Carbon is in period 2. So you have a 1 orbital from the s and 3 from the p, and if you mix them so that they're all evenly mixed, then you get 4, which is what we want because you make 4 bonds. So our previous model, where it's separated, predicts something like this. That's not what we see. We see this tetrahedral shaped again, and this is good if you went and bought the model. This is a good time, during lecture to have it out. And most of what we're going to do is focus on carbon like this. Right, it's not 90 degrees, it's 109.5. All right, so what this VB or valence bond theory is that the electrons reside in these orbitals that are going to be hybridized, and they take on the quantum mechanics stuff that we talked about. And there's this overlap. The same 2 electrons are there, and they overlap these 2 orbitals, and we get a new molecular orbital. Side little note here, the electrons must be spin paired. That just means an up and a down. And then the shape of the molecule is determined by that geometry of the overlapping orbitals. That'll make more sense as we get further into it. All right, hybridize again means to mix, right? You've seen it with a car. Gas and electric is typical when you have a car. So what this does is we get now overlapping orbitals where we can mix all these different ones. And we're going to cover D in here because it does the expanded octet that we saw. But you'll see in OChem you really won't need these last 2. These first 3 are what's critical, right? So if you have an S and a P, or let's say you have 2 Ps, or then 3. And just like before, more bonds has to mean equal more filled orbitals, and that gives you more stability. And what this does, and these slides very much, have a slide here where they put it out in bullets and describe it verbally. Then the pictures are on the next slide. But we already kind of saw this a little bit, how this better explains the shape of the molecules. And here you can see this is, OChem first week. Remember all this stuff for OChem. Carbon wants to form, we saw 4 bonds in any way it can do it. So it's either going to form a single and a triple, which is what you see here for the sp, a single and two doubles, or potentially two double bonds is possible, or four single bonds, sp3. All right, and with every theory, there's little exceptions. So hydrogen, for example, isn't going to be doing any hybridization because it only has one s orbital. It can't reach any p's, so that doesn't make any sense. So it's just s. The number of the standard atomic orbitals combined equals the number of hybrid orbitals. So if before you had an s and three p orbitals, that's four total. The hybridized ones have to be the same as well, right? Four before, four after. The number and the type of the standard atomic orbitals combined determines the shape of the hybrids. We'll see that coming up. That's hard to understand until you see the pictures. A particular kind of hybridization that occurs is one that yields the lowest overall energy for the molecule. That's basically saying the same way the Lewis structure accounted for all the electrons and resonance and how it made the most sense, and thus the lowest energy, and the same thing here for these. Right, and if you know the structure beforehand, then the orbitals, well, that'll predict the orbitals that you need to make that structure. We'll see that they go hand in hand. You can't have one without the other. So little hints or rules to doing this: place electrons in hybrid orbitals and unhybridized valence orbitals as if all the orbitals have equal energy. And again, it'll make sense in a minute. When bonding, these a single bond is called a sigma bond. That's the symbol, and that is when it's between two hybrid orbitals. And then the pi bonds are when it's the unhybridized orbitals that are parallel. This is true. This is going to be hard to see until you see a picture of it. Okay. So, sorry, just moving a couple things. Unhybridized means this is just a carbon atom. This only happens in the gas phase. Like if you took a piece of charcoal and heated it in a vacuum or something. So it basically doesn't exist. You'll never think about it this way, but this is what we taught you beforehand. And now we're saying, well, it's more complicated. Here's the real truth. And the takeaway message here is, if you have a carbon triple bond to anything, this one's bonded to nitrogen, but that's not the issue at hand at the moment. The orbitals on carbon, it takes the single bond, the sigma bond, is with the S and the P, one of each. So the single bond you see here between hydrogen and carbon is one of these sp. Then the other sigma bond that's here between the carbon and nitrogen is again one of the sp. And then these two p orbitals that aren't being mixed are what make up a double, then another bond. And so when there's three bonds, we call it a triple. So whenever you see a carbon, or any element, but our focus is mostly carbon and prepping people for OChem. So whenever you see a carbon triple bond, that carbon must be sp hybridized. All right, same concept here. And right, this Lewis structure doesn't show it, but sp2 means you have three sigma bonds, and then a p left out means you have one extra bond that isn't a sigma. So what that means is the sigma and now this unused p go to make the double bond, right? So the sp2 is each of the single bonds between the carbon, and you get a double bond because of the one p that's left out, right? So these p left out or unhybridized p orbitals are what make up multiple bonds. So when you have two of them, you get a triple. When you have one of them, you get a double. And again, take-home message, carbon that has a double bond has to be sp2 hybridized. Then last, methane, natural gas is a great example. The hydrogens are all the same. There's only one carbon. It's got four bonds. They're all equal. So you need 4 equal orbitals to do that in, and you get there by mixing the S and all 3 of the P, and then energetically they're exactly equal to each other, so it makes no difference between them, they're identical. So this is a really good slide to memorize and know for us, but also for OChem, right? 4 single bonds is sp3 hybridized. A carbon with a double bond, sp2. A triple bond, sp3. So this is actually methylamine. If you watch Breaking Bad or have seen that show, this is the chemical that they stole out of a train, and this is what gets used, depending on how you make meth. Meth and ecstasy are very similar molecules in the chemical synthesis of them, but they both use this typically use this chemical in the reaction to make them. The carbon has 4 single bonds, so it's got to be sp3, and then the nitrogen has 3 single bonds, it's also sp3, but those last 2 electrons, they're still there, but you need the 3 bonds to be equal, and the only way to do that is to have them be sp3, and then the one last sp3 orbital just has the lone pair in it. Okay, then here is back to our orbital diagrams if you think about it energetically. So on the left, and again, here we are, this is typical in science, where they explain and tell you something, and then after you've learned it, they say, well, that's not the full story, it's more complicated than that, and here's the next explanation or the next model. That's what's going on here. So here's our old view of things, and it's still true, but this is only true for an atom of carbon, again, in the gas phase, in a vacuum or something, which is not how carbon exists, right? Almost everything alive is made of carbon. So the carbon's always making bonds to other things. It's not just carbon atoms. Even if it's a diamond or a piece of charcoal, it's still bonded to other carbon. And so we have our hybridization, and the 3 P's come down in energy, the S goes up, you mix them all together, and you get these 4 orbitals that are equal in energy. And so it doesn't matter which one you pick to make a bond, and since they're equal, the electrons spread out, and when you've got 1 electron to combine with any other electron from some other atom and make a bond. All right, that's the energy diagram version. Now here's what those orbitals look like, right? A spherical S, and then the 2 balloons going in the P, going in the X, Y, Z direction. We call them P, so PX, PY, PZ. If you mix the S and each P together, then you get something like this, right? The S was spherical. Each of the P's had this node where the electron never spent any time, so that's why you see that same node there in all of these. And then each one gets a direction along that tetrahedron, and we get the tetrahedral shape. So now another piece of information to add to sort of your memory bank for organic chemistry. Tetrahedral, 4 bonds, sp3 carbon, right? And then here's what we saw on that methylamine, that the nitrogen was sp3 as well, because you needed to make 3 equal bonds. And it turns out just that since there's 1 extra electron in nitrogen, there's 1 orbital, it's still an sp3 that has the lone pair in it. But you still do the same hybridization because you need these bonds to be equal. Right, and then here's that, again, the models. And this one's not the best picture. I think these 3 hydrogens should be, lower down, but this looks like that pyramid where the base is a triangle, right? This is that tetrahedral shape. So methane, natural gas, and then here's ammonia. This is the stinky smell that's in Windex and, mopping solutions and things, cleaning supplies, etc. Okay, then we have those individually, and if we go back to this molecule called methylamine, right, the carbon has 4 equal bonds. A single bond is called a sigma. That's the symbol you see here. So the carbon forms 4 sigma bonds, 3 identical ones to the hydrogen, 1 to the nitrogen. The nitrogen has 2 identical ones to the hydrogen, and then one of the orbitals has the 2 electrons or the lone pair in. All right, if we expand in the periodic table over, we get to group 6 and 7. And so the same thing, this is our same picture, right? We're adding an oxygen, an electron in, so it starts to pair up. And we get those common bonding modes that we saw. Still, you're going to hybridize it. And remember, oxygen wanted to form 2 bonds, a single or 1 double. And so if it's forming two single bonds, the bonds are identical, like water, for example, is H2O. It has to be sp3 hybridized because it's forming 2 single bonds that are identical. The orbitals have to be identical. And the only way to do that is to mix them and hybridize them and have them as sp3. Same argument here for fluorine, or in this example, chlorine, except you have 1 electron left over, right? As we move across the periodic table, you get an extra electron each spot, and so you build up the lone pairs around the central atom. All right, so the sigma bond, or the single bond, is when you have these orbitals that overlap, and it happens directly in between the 2 nuclei. And that's very similar to the picture we saw before, right? The nucleus is positive, the electrons are negative, and they're in between the 2 and hold them together. And basically, these can happen with any orbitals. So if you have S that aren't hybridized, like hydrogen, P, we'll see these coming up. Any 2 hybrids, or like, water or methane, where you have a hydrogen that only has an S and then a hybrid one. Any 2 orbitals, any combination you can think of. So the sigma is pretty straightforward. It's the pi bond that's a touch more confusing and has a different geometry to it. And we'll see the pictures and the geometry coming up on the next slide. The pi bond is what makes multiple bonds. So a double bond is not 2 sigma bonds. What a double bond is it's 1 sigma and 1 pi. And we saw this energetically where a double bond was not energetically worth what a single was times 2. And this is where that becomes more complicated. And the reason for that is because it comes from those p orbitals that we didn't include in the hybridization. Right, and this is what I just said is what this last red bold here is saying. The sigma bond are stronger, and that's why a single bond is worth more than a double bond divided in half. All right, so let's say that there's an atom here at the node, right? Whatever these, these could be sp3 or whatever, doesn't matter. As long as there's overlap between any 2 orbitals, then you get the electrons in between the 2 atoms, and you form the bond. So the sigma bond would be right here in between these 2. All right, so what makes the pi bond is these electrons that are in these p orbitals that are above and below, outside the sigma bond. So a double bond is when you have a sigma and a pi together. You can't have a pi bond without a sigma, right? So what the pi bond does is it just adds energetic bond energy strength to the sigma bond, right? So the sigma is a single, and to get a double bond, you have to have first the sigma and then gain a pi bond. To get to a triple, you have to gain a second pi bond. All right, so here's formaldehyde. Strange molecule, but anyway, here's our old incorrectly drawn, geometry-wise, Lewis structure, right? We know that there's 3 electron groups, and these hydrogens are really pushed back. So what we know now from what we just covered is that it's sp2 hybridized because we have a double bond. So we had to leave one p out. And we know from the VSEPR, with 3 electron groups around it, it's going to be trigonoplanar. So the idea here that doesn't quite get conveyed by the picture is, let's say the hydrogen it's not really above. This hydrogen is supposed to be going back away from you. The red pi bond here is supposed to be in the plane of the screen, right? And then this lower hydrogen is really supposed to be coming out towards you, out of the plane of the screen. So the purple is the sp3 that forms 120 degrees, like the propellers on a plane or on a fan. Then the sigma between oxygen and the overlap of the sp3 make the sigma bond, and then the p orbital that's not being used on the carbon and the p orbital not being used for the lone pairs and whatnot on the oxygen, they overlap, but they don't do it in the same place as the sigma. They do it above and below. All right, and what this does, and this is where the models become really handy because they have this type of restriction in them, is the pi bonds slow or completely stop the bond rotation, but sigmas do not, right? So because orbitals that form the sigma point along that axis, rotation around the bond does not require breaking the interaction. So that means there's nothing restricting a sigma bond from spinning. But the orbitals that form those pi ones, they interact not in the same place. And so they're there and they prevent rotation of the bond. I know that's kind of hard to see. And this again is where the models become good if you bought one. This is good to go back, or if you have them now, make these molecules or watch the video again and do it with the model in your hand. So here, this would be called what? Dichloroethane, and 1,2 because it's on one carbon, and then a different one, they're not the same. And you count carbons in the order of the carbon chain. That's OChem, how you name these things. Anyway, our focus here is that, right, we have 4 single bonds on the carbon, so it has to be sp3 hybridized because we have 4 sigmas. And there's nothing stopping this bond from spinning, either of them, either of the carbons spinning. But if there's a double bond between the carbons, then if you spin these two, the chlorine would flip to the other location where the hydrogen is, and vice versa, the hydrogen will come here, and that would twist these 2 orbitals, these p orbitals, up and down past one another. So depending on how big these, hydrogen and even chlorine are small in this grand scope of organic chemistry. But if you had bigger things there, they would bump into each other and stop the rotation. But the double bond doesn't want to rotate it. If you add energy, so one of the ways they get these things to rotate is you just heat it up, right? You add energy and you can get over barriers. And we saw that a little bit in our chapter on thermodynamics, and you'll see it more in Chem 162. So sort of the take-home message here is that a double bond stops slow slows or potentially completely stops the rotation of this bond, which won't have much effect for what we're doing. We're learning the basics, but you will see this in organic chemistry. And it'll become quite important in organic chemistry. All right, so, a model is better to have in your hand and do this, but, this is a presentation on a PowerPoint on a screen, right? Here's the, space filling spherical ones, and you can just spin the carbon-carbon bond, right? And what that does is it takes the chlorines from being on the same side to opposite sides. But if there's a carbon-carbon double bond there, that you can't spin the carbon atoms. And so what you'll get is you'll get two different looking molecules, where the chlorines are on the same side, and cis means same, trans means opposite, and so the carbons are on opposite sides of the double bond versus the same side. All right, so sp2 is mixing an S and two of the P's, doesn't really matter which two. The point is you get this trigonal planar shape with three electron groups. So if it's for carbon, you'll get a single and three singles and a double bond, but you'll have bonds in all of those, so it gives you a trigonal planar, right? If it's a single and two singles and a double bond, there's three electron remember, single and double bond count the same. They're in three locations, and so you divide 360 by 3, you get 120 degrees. If that central atom is a nitrogen, then one of those locations is going to be a lone pair. So then it would be bent 120, which we already saw. Then for for oxygen, that means it's forming a double bond. It's one and only bond. So kind of end of the story. And that's what this molecule here is trying to show you. It just messed up the color. This, left it as oxygen, but this could have been blue for a nitrogen. But the point is, right, this is bent. Should be blue for a nitrogen. This is bent here. This up here, the red one on top, is the oxygen. And if it's sp2, it must be forming a sigma and a pi, thus a double bond. And then the black is the carbon and it's trigonal planar, right? So linear, if you will, but it's the end of the molecule. Then these light ones here are hydrogen, and then bent, right? So linear, trigonal planar, and bent. And then here's the Lewis structure way of presenting it. They chose oxygen, but you could make this nitrogen and have, if it wasn't a hydrogen, you could do something else with it. Okay, so then what does the orbitals look like for that hybridization? Just like we did for the sp3. This one here is the sp2. So we mix one S, two P's, and we get that trigonal planar, 3 electron groups around the surrounding atom. Then it just depends on what atom it's attached to. Okay, so here's now that look where you get an sp2 coming together. So if it was carbon, nitrogen, oxygen, whatever. The gray is the sp2 hybridized mixing, where we get the sigma. And then the P that was left out is above and below. And so the pi bond that comes from those P's that aren't used, the interaction is above and below. Any way you want to look at it, but the important part is it's outside of the sigma. It's a different type of bond. So this is back to the formaldehyde. Whoops, the formaldehyde one. Right there's our carbon that's sp2 hybridized. The hybridization also matches when it's another element besides hydrogen. So if the carbon is sp2, the oxygen must also be sp2. So the two sp2 orbitals overlap. You get the sigma bond here, just like we did with the Lewis structure before. What's not drawn in here on the oxygen is the lone pairs, and that's fine because the critical thing we're talking, it would just be where these purple ones are. But the critical thing is that it's the p orbitals that aren't being used. So 1 sigma from the SPs, sp2s that are overlapping, and then the p that's left out forms the pi bond, and together a sigma and a pi, what we get and how we describe that is a double bond. Okay, so just like we did before with carbon, the atom doesn't exist like that on its own. So if you have a carbon that's sp2 hybridized, then you're perfectly set up to make 3 equal sigmas. That would, and then 1 pi, which tells you 2 singles and a double bond. Nitrogen, it's going to be the same thing, except you're going to have 2 lone pairs, 2 electrons, 1 lone pair in one of those orbitals. So you're set up to make 2 sigmas and a pi, and what that means is 1 single bond and 1 double bond. All right, so here's similar, but a double bond between the carbon and the nitrogen. Last time, several slides back, it was that methylamine molecule where it was a single bond between the carbon and the nitrogen, right? So just like the last picture, right, here's the orbitals. sp2, so 3 single bonds from the carbon, and then 1 pi bond. So the pi bond makes the carbon-nitrogen bond a double bond, right? A sigma and a pi means double. So a double and 2 singles. The nitrogen then, same thing, but there's only 1 single bond to the hydrogen because of the extra electron on nitrogen makes a lone pair. Okay, so we move along, right? Boron and oxygen, on which are the 2 elements that are on either side of carbon. And this, boron we saw was one of those examples. It was strange and did other things because it's got this empty orbital that it can go do things with. And also why it's kind of fine with its 3 making just 3 sigma bonds and not even taking on another 2. It could have 6 electrons. We saw that from time to time. Boron's a strange example. Oxygen makes more sense, just expanding on the last slide where, right, carbon made 3 bonds, 3 sigmas and a pi, nitrogen made 2 and a pi, and so oxygen has 1 more electron than nitrogen. So we're going to have now 2 lone pairs, 1 sigma and 1 pi. And the same with the bonding motifs that you saw from last chapter, right? Oxygen wants to make 2 single bonds or 1 double bond. And a double bond, again, is a sigma and a pi together. So you can see where we're heading here, right? That was sp3 and sp2. Now we're at sp. And so up here in the blue, right, is the s and the p orbitals. You blend them together, right? 2 areas of electron shape, which means it's linear. The atom uses the hybrid orbitals for the sigma, or lone pairs, whatever, and then uses those p's that aren't used for the pi bonds. So let's say this is hydrogen cyanide. You have a carbon that's sp hybridized, so 2 bonding locations because we have 2 orbitals. The overlap of the sp and the s makes that hydrogen carbon sigma or single bond. Then the sp overlap for both carbon and nitrogen makes the sigma, and then the p orbitals that aren't there make two individual pi bonds. So another mental note is that a triple bond is just like the double bond but expanding. A triple bond is a sigma and two pi bonds. Right, so there's the sigma and then the pi, if you will, above and below it. Same thing here with the orbitals, right? We're just taking one p, so you get these two orbitals that look like a combination between each one. We leave the pi, the p orbitals out of it to make the pi, and this is hard to see, but right, this is supposed to be I don't know, let's call the carbon say the x, then one direction's the y, the other direction's the z. And so again, a lot more going on here in our valence bond model than just the simple Lewis structure. And so we get a sigma and two pi bonds, and that's what a triple bond is. And we can also, again, go back and look at the orbital diagrams of the boxes, right? The atoms don't exist, in the gas phase by themselves. They form molecules. And so the carbon has two of the hybridized ones. So it's set up to make two sigmas and then two pi's. And that either means a single bond and a triple, or two double bonds. The nitrogen's got one more electron, so it's set up to make one sigma and two pi bonds, right? The lone pairs have to be the sigmas. And so then, and then this is what it looks like, right? So HCN, right? The carbon is sp, the nitrogen's sp. The lone pairs have to go in the hybridized. The one sigma goes to between the carbon and the nitrogen. So the two sets of p orbitals on both carbon and nitrogen make two separate pi bonds. And then that last sp hybridized makes a sigma or a single bond to the hydrogen. Okay, so sort of a pause here. Excuse me. From where we started, I forget what slide that was, but to 109, that's sort of your focus here for organic chemistry. 109, and we started. Yeah. 70 to 109. That's really critical. That's your building blocks for organic chemistry. So it'd be good to I don't know if you can download this this video or something, but when you go to take OChem, this is the section here where you'd want to come back and look at this, and this is all the OChem. Okay, so that'll be we'll come back to more of it, but that's sort of the focus for us. There'll be one or two questions on beyond the SP3, but no one will see that again unless you're a chem major. You won't see the hybridization examples for these ones beyond carbon, right? Because that's not what OChem is really about. I mean, they might mention it here and there, but very sporadically. And that's why our last exam, we didn't focus on the things that had 5 or 6 bonds around them, right? These pyramidal, T-shaped, linear. I don't think I put one of those on the exam. They're just not as important. They're important for a chem major in the long run, but almost, it's really rare to even have a chemistry major. And it'll be recovered when you get past organic chemistry and start using these again. But we did talk about the expanded octet. We saw that in the formal charge. We saw that in the Lewis structure. You can see the Lewis structure over here, right? So if you have extra electrons, they have to go in an element that can reach those d orbitals. And the only elements that can do that are the ones that are in the 3rd row or higher. So just like before, remember the double bonds are a sigma and a pi. The way to make something like this is you need to go and grab more orbitals, and the only ones available are those d orbitals. And then just like unused p orbitals made multiple bonds, unused d orbitals can make multiple bonds. And so how do you do that? Just like before, where you blend the ones you need and you leave the ones you don't need out there. So before it was unhybridized P's that were there to make multiple bonds. The thing is now is you have a lot more orbitals. So right, since there were 5 Ds, now you have 4 that you don't use. And we'll see how it can expand and, and that'll what we'll see next. But anyway, so you grab the D, you mix these together, now you get 5 orbitals that are the same. So you're set up to make 5 sigma bonds. Right, so same picture as before, right? Instead of having the S paired up for phosphorus, now you've got this d orbital. You mix them all together and they're all equal, and so you can have phosphorus have 5 things attached to it. Just like from nitrogen over or carbon over to nitrogen or nitrogen over to oxygen, 1 more electron, so you can make the same. You have the same number of orbitals, but now you have 1 more electron, so you're going to get a lone pair instead of 5 equal bonds. We'll have 4 equal bonds and a lone pair. And notice it didn't spend nearly the amount of time showing you examples and marching through it. And we get all those same shapes here. And now we're moving on and just grabbing 1 more d orbital. But the concept is the same. So if you want 6 equal areas or 6 electrons, or whether it's 6 bonds or 5 bonds and a lone pair, it doesn't really matter. You need an orbital to put them in. So if you need to make 6 bonds, you're going to need 6 orbitals. And then just the same picture here, but they just grabbed another one, right? And don't worry about the geometries. I'm not going to put one of those on the test. It wasn't on the last midterm. Again, only chem majors are going to see and use these again. And then there you got the d orbitals left. So if you need to make multiple bonds, you got orbitals left to do it with. Right, so the only difference is here, and these are, here's sulfur and then iodine, right? If we're mixing them, now they're equal in energy, and so our 6 electrons can now spread out and make 6 equal energy orbitals. And so you can take something like sulfur and attach 6 things to it and make 6 even bonds, right? Iodine's 1 over, so the exact same principle, but now you have an extra electron, so you can make 5 equal bonds and then have a set of lone pairs on the central atom, in this instance, iodine. Okay, so a good table to look at. OChem is going to focus on, 2, 3, 4, because that's carbon. You'll see a little bit of sulfur and phosphorus stuff, which can be bigger in those octahedral and bipyramidal, these sp3d and sp3d2. But these won't really be used. I'd say like OChem is going to be 99%, 2 to 4 tetrahedral and up, and 1% they'll talk about in CVs, but it just maybe less than 1%. It's not as important. Those bonds are, those elements that can do this are not the critical thing in organic chemistry. Okay, so just a couple of examples here now. Borons are exception, right? It doesn't need 8 electrons. So here's our Lewis structure. Hydrogen can't hybridize, end of story. Oxygen's got 4 groups around it. So you need 4 orbitals to do it in. 2 single bonds means 2 sigmas. Those are made with, and they're equal to each other. So those are made with the sp3. And then boron's a weirdo. It doesn't need 8 electrons, but since there's 3 groups around it, and the bonds must be equal, right? Each boron-oxygen bond is identical. And so we only need to mix 3 orbitals, and the leftover p orbital on boron isn't being used in this example. Remember, boron's kind of strange. All right, O NCO was an example last chapter when we looked at shape and polarity. So this is how it's drawn. Lewis structure wise, when you're doing it in Word, you can't show that. You have to have like a computer or a chemistry program. But here's what it really looks like, right? That bond is shorter because it's nitrogen and oxygen, smaller atomic radius, right? Group 2 versus a group 3 element. It's a multiple bond, a sigma and a double. So it's stronger and shorter for 2 reasons. We've got to have 3 equal orbitals for the nitrogen, right? Because it's forming 3 electron groups around it. And a double bond, again, hammer home, means sp2. The double bond's happening between both elements. So the oxygen and the nitrogen have to both be sp2, but the chlorine has 4 groups around it that are identical. It's just that lone pairs are in 3 of them and only 1 bonding, but they're still sp3, right? There's 4 equal groups. Okay, so here's how you can really see these 2 chapters are really one big giant chapter, right? So to draw a molecule and know everything you need to know about it for, correctly and again, prepping you for OChem is, draw the Lewis structure, which, that I know that's just step 1 here, but which has multiple steps in its own, but we did that last chapter. Then we expanded from there. We use the VSEPR, that's sort of the balloons tied together, gives you the space filling, the electron pushing, and that tells you the geometry. Right, then from the geometry, the electron groups around it. We know what kind of hybridization you need to make that type of electron group around it. Then if you want, you sketch the orbitals on that, and you can show what kind of overlapping there is, and that'll get you to whether the individual bonds are sigma or have pi bonds. Any bond has to have a sigma. All right, so here is F-aldehyde. So when you drink alcohol, you have an enzyme in your body, in your liver, that oxidizes the carbon from an alcohol, an OH, to a carbon-oxygen double bond. Our carbon 1 has 4 single or sigma bonds, so it must be tetrahedral. It's got 4 equal groups around it. Our carbon 2 has a double bond, so we've got to leave 1 p orbital out. It's got 3 bonds or 3 electron groups. It's trigonal planar, and that means that carbon 1 is sp3, carbon 2 is sp2, and then it didn't include it, but the oxygen must also be sp2, right? Because it's got a sigma and a pi bond. If you have a pi bond, both elements making the pi bond have to have a p orbital that is unhybridized. They have to have that same hybridization to make the bond. So here's the full story of everything we've covered the last 2 chapters. And notice here, this is for OChem people. They stop drawing the lone pairs around elements like oxygen that have them. They're going to assume that you know how many electrons oxygen has, and the carbon-oxygen double bond's the key part, and that obviously implies that the lone pairs are there, and they're going to stop drawing them. Let me see here. Yeah, we have enough time. So there's one more theory, one more expansion on these things. And just like before, we're like, oh, here's this theory, works pretty good, but that's not the full story. There's more to it. So our valence bond theory that we've talked about and discussed here isn't the end of it. There's some properties that it like valence bond was better than Lewis, but there's still some of these things that implied here in the beginning, that magnetism, paramagnetic versus diamagnetic, that it didn't fully explain. So from valence bond, we're going to talk about MO, or molecular orbital theory. All right, so what is MO theory? Again, not a history task, history class, or a history exam. As you've seen, Schrodinger is just that name of the famous physicist that we saw on the quantum mechanics. And the electrons move throughout the orbitals, and so we get this whole molecular orbitals. The electrons belong to the whole molecule. So it's kind of different, where valence bond was just putting them overlapping and saying that's it. Electrons move, near the speed of light, and kind of like the resonance, like the electrons could flip-flop and move back and forth. And we'll see as you move along that changes in a molecule, electronegativity and whatnot, of it swapping an atom or anything, has an effect on the electrons and the bonds through the whole molecule, not just at the site of the bond. Also remember that electrons have wave-particle duality. And so this next, I don't test you on these names, but LCAO is linear combination of the atomic orbitals, which is, combining, gives you the M molecular orbital. And remember that electrons have that wave-particle duality, so that means that they can, you can think about them as combining constructively or destructively. And so constructively means you form a bond. And the bonds we already talked about, we saw those, right? A sigma and a pi. The sigma meant single bond, and then a sigma and a pi together meant a double bond. Well, that's the constructive form. Then anti means opposite. So that's bonding when they overlap in a positive way. And since they have wave-like features, they could overlap in a negative way, and that's called antibonding. And that's this little star symbol you see here. So the bond before, it's called sigma and pi. This is called sigma star and pi star. The sigma and the pi was the electron density was between the two nuclei, so it held them together. So then the antibonding one must be where the electron density is outside the nuclei. So in the simplistic form, this would be hydrogen. Hydrogen has one electron and a 1s. Here's the orbitals. Sounds like a police car going by. Wait a sec. Okay, so constructively is where they come together and they overlap, and the electron can spend time in between the two nuclei, and it makes a bond, which we know is beneficial and lower in energy, and that's what we see. So the opposite would be where there's no overlap between the two, and the electron spends more time on the outside. Electrons in MOs that are stabilizing, that's the constructive, that's lower in energy. So if one is constructive, the other must be destructive or destabilizing. So that means that those orbitals would be represented as higher in energy. And again, they're outside the nucleus, because that's not what's the inner nucleus axis, because that's not favorable. Electrons in antibonding orbitals cancel the stability by electrons in the bonding orbitals. And that really won't make sense till you see the picture. Okay, bond order is just like kind of what we already covered, except you can have half values. So bond order, a single bond, the bond order would be 1. A double bond, the bond order would be 2. As usual with all this stuff, we're only considering the valence electrons. But now with our resonance and radicals, you can get a half an electron, right? So when it's saying here, it may be a fraction, it doesn't mean a third or fourth. Well, it could mean that, but let's start off with a half, which is more common in what we'll cover, like a radical. So 2 electrons make the bond, and then if there was the radical 1 extra electron, that would give you a half order. There's a fire station up the street from me, and the first siren went by really fast. That's obviously a police car. And then the fire truck takes long. Okay. The higher the bond order, the stronger, and the shorter the bonds. We already knew this from last chapter, right? Single bond versus double bond order would be 1 versus 2. It's stronger, it's shorter. Nothing different. Bond order equals 0 means there is no bond. There's nothing going on. And that'll make sense once we see the picture. So now, when we see these pictures, you can see that this is how molecules have unpaired or completely paired electrons, and explains the electronic features and the magnetic features that are seen in real molecules. All right, so these two, these couple of bullets explain all this, and then here's the simple math behind it. Bonding versus anti-bonding and divided by 2, right? Because a bond was 2 electrons. So if you had 2 electrons divided by 2, that equals 1. So a single bond has a bond order of 1, 2 divided by 2. Okay, so now here's the picture where this makes more sense. So let's start with the easiest example, hydrogen, right? If you have a hydrogen here, and on the outside are your just the hydrogen atoms, and then on the inside is what happens when you mix the 2 atoms together. So hydrogen only has the S. These are these orbitals. They're where electrons are moving. Remember, wave-like function, constructive and destructive. So constructive is going to be lower in energy. Destructive, or the anti-bonding, is higher in energy. Your total number of electrons on the outside has to equal the total number of electrons in the middle. So 1 plus 1 is 2. So you put 2 electrons in, and we see that we get 2 electrons in a constructive, lower in energy bonding, none in the anti-bonding. So this would be 2 divided by 2 equals 1, which is what we already knew from the Lewis structure, so it matches. Right, and here's what our hydrogen looks like, right? The bonding, it forms a single bond. And then the anti-bonding one that you don't see, but now are aware of it. All right, so that's the easiest example. And you will see this in organic chemistry, a bit of this type of MO, right, molecular orbital. Then HOMO versus LUMO here, it stands for highest occupied molecular orbital, and then lowest unoccupied molecular orbital. So in hydrogen, it's really simple because there's only 2, but this would be, this sigma here is the highest. I mean, it's the only one, but we'll see how that becomes. There's more options as the molecule gets more complex, and that this is the lowest. And why is that important? Is because if you flash enough light and do something to break the bond, what that does is that's forcing this electron from a bonding up here to an anti-bonding. And the distance between these two is that the wavelength of light that it takes to break that bond apart. Okay, so here's helium, right? And helium, we've already talked about it, just first memorizing it, and then Lewis structure. It doesn't form a bond. Why not? Is because on the outside, each helium has 2. So 2 plus 2 is 4. here's the sigma and the sigma star. When you put 4 electrons in, you get 2 bonding and 2 non-bonding. So 2 minus 2 equals 0. You divide that by 2, you still get 0. A 0 means there's no preference and no reason for it to form a bond. And we don't see helium making any bond. It's a noble gas that's fine by itself. Right, as many electrons in the antibonding versus the bonding, so the net effect is no bonding, nothing happens. Okay, so if we move on to lithium, the 1s, just like helium, cancel each other out. That's not beneficial. And what happens next is just like it was with hydrogen, but it's the 2s. Now there is a bonding effect, which means the lithium would like to make a bond. Now it's not a non-metal, and it has other reactivities, so it does form a metal, but it's also reactive. But this is what it would look like, right? 4 minus 2, because we have 2 electrons in each of the sigmas, and then 1 in the sigma star, or the antibonding. So bonding minus antibonding divided by 2. And this is why you can have lithium metal. Right, and the picture looks the same as it did for hydrogen. It's just the bond is longer. On the same HOMO and LUMO interaction, because they're right above and below each other in the periodic table. Okay, so that was the s orbitals overlapping. But that's really a short story because it's just hydrogen and helium. Helium doesn't make a bond. So it's really, and lithium's a metal. And so that's really just hydrogen, basically. So everything else has p orbitals. So what happens as 2 p orbitals overlap with one another? Same thing, you get a positive and then a negative, a bonding and an antibonding, constructive and destructive. And the antibonding orbital should look just the opposite of the bonding, right? So in the bonding, the overlap is bigger in the middle with these smaller lobes on the outside. And then the antibonding, the lobes are bigger on the outside, smaller on the inside, and actually a node or a spot where there's no interaction between the two. This is when they're directly overlapping between each other. So this would be the sigma bond of a multiple bond, sigma bond of a double bond, and then the pi bond, right, is between the p orbitals that are sticking out and don't go directly between the 2 nuclei. So the bonding was above and below, and the antibonding then should never have the orbitals never interacting in between the 2. So something like this. All right, and so this is, well, I mean, the class is online, so this is too tough to do. But what they're trying to show you here is if you take oxygen and you compress it and cool it down, you can turn it into a liquid. And what you see here is 2 magnets, 2 really powerful magnets, and they're held apart, by, they're bolted in this way so they can't stick to each other. But you have 2 magnets that are attracted to each other. If you pour liquid oxygen, it'll freeze and solidify where it's held here. And what this tells us is that oxygen O2 is paramagnetic. And an only way for it to be paramagnetic is to have unpaired electrons. And the Lewis theory and the valence bond theory both don't predict that. And so here's the classic example of why you have to learn and MO theory is useful. So on the left is everything we talked about that got you to the Lewis bond theory. On the right is the valence bond that explains quite a bit more. And now let's do the MO. So the 1s we can ignore because they perfectly cancel each other. And really the 2s do that as well. So what really explains the P, the magnetic property, is up here where, right, we have the 4 electrons in each oxygen atom in the P. So you get a sigma that overlaps and is positive, a pi, the two p orbitals leftover ones that overlap, and you form those pi bonds. And constructive overlap is lower in energy. Destructive one gives you the antibonding orbitals and higher energy. And same number of atom electrons on the outside. So 4 and 4 is 8. So you plop these in and you get 1, 2, 3, 4, 5, 6. And then here's those unpaired electrons in the antibonding orbitals, electrons 7 and 8. So the bonding is the 8 electrons that are lower, right? 1, 2, 3, 4, 5, 6, 7, 8. And then the antibonding, the sigma star here, and then the pi star, right? These two electrons and these two. So 8 minus 4 is 4 divided by 2 gives us a bond order of 2, which we already knew from the Lewis, right? A double bond and valence bond matched, a sigma and a pi. But now molecular orbital theory explains the magnetic behavior. Excuse me. Right, more electrons in bonding than antibonding. So we know we get a net bonding interaction. We already knew it was a double bond. But the critical thing here is this theory explains that unpaired electrons, that paramagnetic behavior that we see. I won't put these orbitals, what, bonding versus antibonding, what they look like. You might see these, you will see these in OChem, whether they test you on them, I don't know, that you'll cross that bridge when you get to it. Again, HOMO means the highest occupied molecular orbital, and LUMO means lowest unoccupied, and MO is always molecular orbital. Okay, so let's do an example. Nitrogen gas N2 is 1 over from oxygen, and so it's going to look really similar. But since it's got 2 less electrons, it fills up the same except right here, right? We don't have those electrons in the unpaired, in the pi star, in the antibonding orbital. So nitrogen doesn't have any magnetic character. And now we've got 2 less electrons in the antibonding orbital. So 8 minus 2 is 6, divided by 2 is 3. And that's what we already knew from the Lewis structure and the valence bond theory, that it was a triple bond, right? 1 sigma and 2 pi. Right, so those 2 electrons are gone from that orbital that's the same, and that's why it doesn't have the same magnetic character. So this theory, MO theory, works really well for explaining differences between 2 gases right next to each other, nitrogen and oxygen, that look nearly identical via the Lewis theory and the valence bond theory. Maybe that's the ambulance. I don't know what's going on. So not enough time to finish this. There's not many slides left, but I know this theory is a bit more complex. So we'll pick up here on Monday. I'll go over this again because I know it's kind of tricky and different, and it's weird than everything else we've done. And it gets more complex as we go. So sorry, just moving a couple things. There. Okay, so we'll pick up here on Monday. We'll finish it out, and then we'll do some worksheets once we're done with this. And then that's Monday. Then Wednesday is our last day of class, where we'll do the study guide, depending on how long that is. I think the final exam study guides that I put up are a bit longer, so I don't usually finish those in a whole 50-minute period, let alone an hour and 15. They're pretty long. Okay, so that's, we're over time. So feel free to take off or hang around if you got any questions, comments, thoughts, feelings, etc.
The final is Wednesday, right?
I'm pretty sure. I'm not 100%, but I'm pretty sure. I forget the time, but I'm like 95% sure it's on Wednesday.
I think it was like 11:50 because it's earlier.
Yeah, that sounds right. It's on the syllabus, and then you can find it on the internet if you just Google, like, uh, final exam times, Hawaii, CC, etc.
Okay, so we basically have two more classes, and that's Monday, Wednesday, and we're gonna go over the final study guide and whatever worksheets we haven't gone over yet.
Yeah, because this last part here will only take 15 or 20 minutes. So we'll have, 30, 45 minutes or something next Monday. So we'll do some worksheets, or if there's anything people want to cover, let me know. But otherwise, I'll just pull up some of the worksheets we haven't seen yet.
Are we gonna cover chapter 11?
No, I just put chapter 11 in because it depends on where you take Chem 162, or like, if you transfer, wherever. Some books and like UH Manoa used to try to push and do chapter 11, 1 through 11, and then they did 12 through 20 in Chem 162. But, here we are with not much time left. I don't think we'd have time to cover a whole nother chapter. So I put 11 in there just for you if you want it, with depending on what you do for Chem 162. Yeah, but we don't have time to cover it, and most people don't, and so it just depends on what class you end up taking next, and where that instructor likes to pick up, and depending on where they left off, et cetera, et cetera. So
Yeah, all right, okay.
yeah.
Well, have a good one. Look forward to seeing you on Monday.
All right, cool. Have a good weekend. See you Monday.